Hello, today I'm going to be talking about scheduling of business transactional processes in a digital supply chain. So to give some of the insight behind it, if we look at some business processes that are common in most supply chains, such as the order to cash process, which describes the sequence of transactions that must occur between when a customer places an order until the goods are delivered and the cash is collected for those goods that were sold to the customer. There's definitely some improvement potential. This is a sample histogram showing the days to process and ship an order on the x-axis and then the count on the vertical axis. So we can see most orders don't take too long, but there are still some orders that take quite some time. And so there's quite some spread here in this histogram, which shows that there are some inefficiencies in the supply chain which ultimately impact the experience that customers have and the economics of the business. So the idea of the research that I'll be presenting today is trying to find ways to improve the performance of the supply chain and perhaps reduce some of this variability and improve that customer experience that lots of companies are targeting. So if we look at a supply chain, there are three main types of flows. We have material flows going from suppliers to manufacturing to distribution centers to customers. We have financial flows. We have information flows as well that are being stored in that, what you would call that digital supply chain. And the enterprise resource planning systems such as Oracle and SAP, there's a lot of information that's stored for each of the transactions that's occurring behind the scenes in the supply chain. So the motivation is, can we integrate these business transactions in the more traditional supply chain optimization, which is focused primarily on the flow of materials. So now we want to look at this flow of information from an optimization perspective. So what I've shown here is a sample schematic for the transactions that are occurring behind the scenes. And so there's quite some complexity there, different steps going back and forth between when the process starts until the process ends. And the goal is, can we develop an optimization model that will schedule the transactions in coordination with the supply chain operations? So something that was observed by the folks at Dow is that there are a lot of similarities between these transactional business processes and chemical batch processing. So if we look at a business transaction where there are several steps that an order needs to go through, and if we compare that with a batch process where once again there are several steps that a chemical plant needs to go through when producing these batches of chemicals, there seems to be a good analogy between the two where we could associate an order with the concept of a batch, and the business process could be viewed as a multi-product or multi-purpose batch plant. And so the problem statement is, given a set of orders with due dates in the transactional network, can we determine the optimal sequencing of orders to be processed so that we can maximize the customer service levels? So the basic idea is, can we exploit this analogy between business transactions and batch processing and use mixed integer linear programming scheduling models, which are used frequently in the chemical industry, and apply those to business processes. So the work I'll be showing today gives a survey of some scheduling models that are available in literature, comparing discrete time and continuous time models, precedence models, and network models that can be used to schedule now business transactions, and I'll be talking about the performance of these different models. So modeling simplifications for this initial phase of the research is that the problem is viewed as deterministic and there's an ideal transactional path. So order reprocessing and exceptions are excluded for now. So in order to perform this research, one needs to have a mathematical representation of the process. And so the approach taken here is that of a queuing network, where there are several stages or tasks or transactions that need to be performed on an order. And once the orders come in the system, they go to the first stage and they gradually move down. But at each stage, there is a queue that's associated with the stage or with the agent that's available at that stage, where we can have one or multiple agents performing certain transactions. And so the order gets in line in the queue and then gets processed eventually and moves down to the next queue, and so on and so forth. So for queuing systems, traditionally, they're viewed either as first in, first out queue systems or priority queue systems. So the first in, first out just means that the orders are processed as they come, and in a priority queuing system, there are some priorities assigned to orders. Where we can have a queue, we have the service node with the agent, and then they move over to the next stage. So the idea here is, can we look more of a bigger picture, look at the different customer priorities, due dates, how long it takes to process these transactions, what resources are available, what orders are active, any forecast of orders, and use this information to get a more big picture assignment of priorities, which I would call the enhanced priority queue. So priorities are assigned to orders in each of the queues in the system based on this bigger picture, which you could think of as when the optimization is done, or when the scheduling is completed, you're in essence shifting the positions of the orders that are in line in this particular queue. And you're doing that for all other queues. So first, I looked at some continuous time models where we have the queue slot model, which is based on the time slot model by Pinto and Grossman, and there's the general presence model by Mendez and Cerda. And in these continuous time models, we have some binary variables indicating the assignment of an order to a certain position or to a certain queue for a certain transaction. We have the start and finish times. We also can have precedence relationships. So for instance, we could have that order A in stage 1 needs to happen before, or will happen before, order B in stage 2. So this precedence relationship of X would equal to 1. Or we can map these schedules onto a queue slot sort of framework where we have certain positions in that queue for each of the agents, and they get filled up. On the other hand, the network models, such as the RTN or STN, the Resource Task Network or the State Task Network, they focus more on a resource or a state balance, which is a concept that's very familiar to chemical engineers, where when we do material balances, we know that we have consumption, generation, arrival, exit. We have the value at the previous time step, and then we get our new current value. Now, some trade-offs between continuous and discrete time models are the continuous time models are more accurate, they're more flexible. You do need to, however, identify the number of time periods when you're working with continuous time network models, and so that can be tricky at times. This leads to doing some sort of approximation when you have entrance or exit of resources or states. So for instance, if order A is arriving between these two time points, you need to do some approximations to assign it to one or the other. A disadvantage of the continuous time models is that the linear programming relaxations of these models are not tight. However, these models are smaller. On the other hand, the discrete time models, they are approximations because time is not discrete. There can be some issues with resolution, so how fine should your discretization be? You also have the advantage of monitoring states and resources at specific time points, and the linear programming relaxations are tighter. However, the models are larger, but usually these tightness of the relaxations overcomes the disadvantage of having larger mathematical models. So I would like to show some results on a couple case studies for a small instance of the order to cash process where we have 2 or 3 main transactions, the CSR processing in order, we have 1 agent available, we have inventory available at 2 different sites, and then we have the execution of logistics. So in a system where we have these 4 different agents, each with a specified processing time, and we have 10 orders come in at different dates and with different due dates, different revenue values, and also different penalties for not fulfilling the order on time. Now, if we run the scheduling models with this, we see quite some differences in the performance of the models. So, for instance, our general presence model, which is a continuous time model, finds the true optimum, and it does it at a relatively quick amount of time compared to the other models. The continuous time network models suffer a bit, and so what I'm showing here, I have the objective value in red and then the CPU time in blue. So they end up clocking out pretty quick. And the discrete time models don't reach a good optimum at first when the discretization is coarse, but as you make the discretization finer, you get very close to the true optimum, and with a slightly larger computational time than this general presence model. We can look at the different model sizes, so definitely the general presence model is smaller than the discrete network models. Now, if we look at the Gantt charts for the general presence model and the discrete time STN models, we can see that most of the orders are scheduled within the time window, which are these orange bars. The different transactions are scheduled within those bars. And one of the results is that there's about a 10 to 15% increase in profit relative to a first in, first out system. So we see that there are benefits to using scheduling of these transactional processes rather than running an unoptimized system. Now, for a larger instance where we have 10 different stages, 3 agents assigned to each stage, and we look at a 30-day horizon, 2 subcases were run, one with 20 orders and then another one with 10 orders. On the 20 orders, there's comparable performance. The general presence model does find a better optimum than the discrete time STN, and we can see that the computational size of the model is something that helps the general presence model here. However, when we increase the size to 50 orders, due to the lack of tightness in the linear programming relaxation, the general presence model suffers and it times out after an hour, whereas the discrete time STN model finds a solution with a 2.6% optimality gap. And a very interesting thing here is if you look at the original model size, you have the constraints and the binary variables, continuous variables. After the pre-solve that is performed with the commercial solvers, the size of the model is reduced significantly. So from about 1 million constraints, it goes down to 5,000 constraints, and 500,000 binary variables, a couple, 20,000 binaries. So the commercial solvers do a great job reducing these sizes. Something I'd like to point out, though, is that although this problem was solved with a time limit of 1 hour, it explored about 11,000 nodes in that time. However, in the first 128 seconds, so the first 2 minutes of computation time, before branching, so at the root node, the optimizers were able to find a 3.4% optimality gap. So there are good feasible solutions that are found very quickly at the beginning of the run. Some conclusions in future work are that optimization models from manufacturing systems can be applied successfully to business processes, and Scheduling these orders can increase both the profit and the customer satisfaction. The discrete time STN model applies well to these systems. There was a 10 to 15% improvement observed in the small instances relative to an unoptimized first in, first out system. And there's opportunity to extend these types of models to additional system complexities, such as having parallel events. So there may be transactions that can occur in parallel, introducing uncertainty in the processes, where there can be a variability in the processing time. There can be order exceptions, so there may be alternate paths in a network of tasks. There may be recycle loops. And so looking at perhaps applying these models to a sort of dynamic optimization with a rolling horizon is a good direction to move forward. And also looking at large-scale solutions. So in the industry, these systems are much larger than what I've shown here in the case studies. So there is a need to do the scaling to these larger problem instances. With that, I'd like to thank the support of the Center of Advanced Process Decision Making at Carnegie Mellon University and also Dow. Thank you.